So welcome back, everybody, and welcome to this session on September the 29th. The topic today is to bring up, obviously, a repetition from what we did last week with some of the basic elements where we rewrote the Hamiltonian operator in terms of the new vacuum states. And we introduced this notation with a lettering for particle states and states below the Fermi level, which are normally called host states. They're all particles, but we normally label them as particles and hosts. Some people would sometimes call them passive states and active states, depending on the context. And you may find different definitions in different fields. Then we are going to look at the diagrammatic representation of some of the terms. The diagrammatic representation is something which will be more powerful when we come to methods like many-body perturbation theory, and also copper cluster theory and so-called post-Hartree-Fock methods. But we are going to bring up some of the rules. And then we are going to start with the first many-body method. And this is what's normally called full configuration interaction theory, which simply means that we are going to set up the Hamiltonian matrix and we are going to diagonalize. And if we can diagonalize, we have actually solved the many-body problem. And tomorrow, on Friday, we are going to pick up again this Lipkin model, and we're going to see how we can construct the basis of states with these quasi-spin operators, which we saw in the exercise for 3 weeks ago. And then we're going to diagonalize the problem, and then we're going to make interpretations. And hopefully that allows you to gain and build up your own insight about a solution of a many-body problem. Then, since in most cases we cannot diagonalize, what is the standard recipe or the standard route is that you would deal with so-called approximative methods, where you can either in systematic ways or in kind of more ad hoc ways, like many-body perturbation theory, where you don't know whether the theory converges or not. You can build up correlations, which you have in the full configuration interaction theory. And when we are going to develop the theory today, we are going to also rewrite the equations in a non-practical way. But that non-practical way is going to give us a link with other approximative many-body methods, which are normally called post-Hartree-Fock methods, because we will also next week introduce an approximation to the many-body problem, which is called Hartree-Fock theory, which belongs to the class of mean field theories. And that is in essence you rewriting the diagonalization problem in terms of coupled single particle equations. Okay, so let's quickly remind ourselves of what we did last week. And one of the exercises tomorrow deals actually with you practicing and rederiving the equations which we did last week. So we have a new vacuum state. So what comes now in the next few minutes is basically a recap of what we did last week. So we have a new vacuum state, which we sometimes label with a C, or sometimes we just label with a phi 0. And this is our quantum mechanical ansatz for the system. And typically, since we're dealing with fermions, we would define a Fermi level, and then we have states up to this Fermi level which are occupied. So we have single particle states up to a given number, and this number is normally n, the number of particles which we have. So this phi of 0 is an n-body state. And that determinant is unique because we are filling up all the single particle states up to a given level. So there is no permutation possibility. And that defines our Slater determinant, this phi 0, or the vacuum state. And we have a labeling here where we label these single particle states with labels I, J, K, L, etc. Then we have states above the Fermi level, which are empty or they are not filled up, but they can be filled up by kicking out one of the particles from below the Fermi level to above the Fermi level. And these states are states which we label with A, B, C, D, etc. And then we have a generic labeling for all the states, P, Q, R, S, etc. And when we are running out of letters here, we will typically have an A1, A2, A3, and so on to indicate that this is a state above the Fermi level. And if you have an I1, I2, and so on as a state below the Fermi level. Now, what we did then was to actually rewrite the Hamiltonian with a new vacuum. And we had a one-body operator, P of Q. So P and Q are now generic states. It can be below or above the Fermi level. And we have the creation operator, AP, and an annihilation operator, AQ. And then we had the matrix elements of P, and I have to redefine this operator V here. Now, F plus, and then we have a term, which since we are using, I use normally anti-symmetrized matrix elements. That's a compact way of putting up the so-called direct term and the exchange term. And this runs over P, Q, R, and S. So we have a matrix element. And it's common to actually put a kind of labeling around these creation and annihilation operators to indicate that these are normal ordered operators with respect to a new vacuum. At the end, you just skip that. Some people use a column, and you'll probably see that in different texts depending on the different authors. So I've been following the notation which is in the textbook by Shavit and Bartlett, and they use this kind of notation to indicate that these are these operators with respect to a new vacuum state. So these are anti-symmetrized matrix elements. And often people, as we mentioned in the beginning of the semester, people tend to drop the AS because you can deduce that from the factor 1 divided by 4. And this contains now the creation and annihilation operators for a two-body operator. Then there is a additional term, which we label as E0 for the reference energy. So we rewrote this in terms of an operator F of n, where F is now a one-body operator plus the two-body operator plus this E0 reference. And this, just let me remind you quickly of what this E0 reference is. This is the sum over all the states below the Fermi level. So when I write a letter like I, it means implicitly that these are only states below the Fermi level. And this has an I, and this expectation value of the one-body operator, which we have, which now contains kinetic energy plus an external potential. And then we had the two-body term, Ij, and this has an anti-symmetrized matrix element, Ij anti-symmetrized. I'm trying to put hats on all the operators here. That was a definition of the reference energy. And this is nothing but us calculating phi 0 of H with phi 0. So this is this expectation value. So often you would choose a basis where you hope that this E0 ref is as close as possible to the exact energy of the system. And in that case, you have a pretty good approximation, and the rest of the correlations which you want to bake in are then determined by these other operators. Let me also remind you of this F of n. This operator is given by the sum over the one-body terms. And in this case now, I am assuming that this basis P and Q is not necessarily an eigenbasis of H0. Normally that is the case. So you would choose an eigenbasis, which is a basis of that operator. And that means that this would reduce the diagonal matrix elements. But we just leave it like this because Fn could be replaced by another one-body operator. And then we have AP, AQ. Then when we normal ordered the two-body operator, we got an additional term, which now modifies the motion of the particles due to the states below the Fermi level. So you can think of the states below the Fermi level setting up a kind of field which the other sees when they're moving around here. So this is a P of I, of D, and then we have a Q of I, and then we have these operators AP, AQ. So the operators are always normal ordered. And from now on, I'm going to skip this notation with the curly brackets. So this is one of the things you're actually going to deal with in the exercises tomorrow, just to convince yourself that you get this expression. It's not an exciting exercise, but it's useful to have seen it. Then what we did was to define a new Slater determinants, IA, so which is now an excitation of the type one particle, one hole, with respect to the vacuum state. So this is a one particle, one hole excitation. So this is a typical way we would label these types of excitations. And what it means is that you would now excite the system, the particles are interacting, and then you have some excitation. You pick out this specific state here. You leave a vacancy, so I'm just making this, coloring this black, and you will promote that one above the Fermi level here. So that's an example of a one particle, one hole excitation. In principle, since this single particle basis is an infinite basis of orthogonal functions, normally we would choose that as basis with orthogonal functions, then this basis here should have an infinity of one particle, one hole excitations. Then what we did as well was to look at the possibilities of having a two particle, two hole excitation. And this is something which we would write as an A dagger, a B dagger, and then we had an AJ, then AI, in order to make this anti-symmetrized to phi 0. So this is typically a two particle, two hole excitation. Then you could continue like this. And now we need a slightly different labeling. So we could have an I1, I2, up to IN. So these are now the states below the Fermi level. And then we have an A1, A2, up to AN. So this is obviously given by an A1 dagger, A2 dagger, up to an AN dagger. And then we have an AN, AN minus 1, down to A. So, sorry, this is I and I here, and I1. Sorry, I was a little bit rushed here. I have too many subscripts. Let me just rewrite it. So we have an A1 dagger, A2 dagger, up to AN dagger, and then we have AIN minus 1, and down all the way to I1, acting on the vacuum state. So this is an example of an N particle, N hole excitation. So if you have 10 particles, you can produce up to 10 particle, 10 hole excitations. So when you're now redistributing your particles in these single particle levels with the replacement, because this is what follows from the Pauli principle, then you can rewrite your basis of Slater determinants in terms of these particle hole excitations. So that means that if we now have the ground state, the true ground state, which we are aiming at, in that specific case, what we have is a state psi 0, and this is now going to be given in terms of a linear expansion. So we would have a Cj0, and this is multiplied with the set of Slater determinants we have. And now I haven't made a specific grouping of them. So this Cj0 is actually the element of a unitary transformation. So that's the elements of a unitary matrix when we are transforming from one basis to another. And since the operators are Hermitian, we always deal with unitary matrices. If everything is real, we will typically deal with orthogonal matrices. So these C's are just matrix elements of a unitary transformation, and they are given by the overlaps between these two states, psi 0 and phi j here. So since we don't have psi 0, it means that we need to find a way to find the C coefficients. And this is what the many-body full configuration interaction theory is going to give us through a diagonalization problem. So we're coming back to that. So actually what we are going to do for large fractions of this course is to find methods to find these coefficients. So the basic approximation is that we have, so I'm reminding you a little bit of what we said in the beginning of the semester, we have a computational basis, which you can define because often the computational basis is given by the single particle states, which are the solution of a known problem. In our case, this is this Hamiltonian H0. And with that, you can construct a basis here, which we call the computational basis. Whether that's a good basis or not remains to see. And since this is now an orthogonal basis, we can then expand the true state, or the true eigenvalue state, in terms of this computational basis. And the different many-body methods, they actually deal with ways to calculate this. So many of these methods which we are going to look at, they are called wave function-based methods. And you see that immediately because we have a wave function model again. So wave function-based models. You could say that Monte Carlo methods, where you make an ansatz for the wave function, is also wave function-based. You have methods which are not based on that, but we are not going to cover those methods here. So essentially all the most important many-body methods, where you're doing Green's function theory, couple cluster theory, density functional theory, Hartree-Fock, they're wave function-based methods. So you have a computational basis. I'm just repeating these things because sometimes it is easy to forget it. And this is also going to give, when we've done FCI theory, it's going to give us a link with approximative methods. So if you can diagonalize, you're done. This is a little bit like when you do fitting of functions. If linear regression works, ordinary square works, you use that. You don't cook up more fancy methods. So if you can diagonalize and can solve the problem, then you're fine. Which is never the case, by the way. Okay. Except for some simple cases, like the Lipkin model and other schematic models. Okay, so life is not meant to be easy. So one of the things which we saw now, just as a repetition, was this expectation value here. Let's remind ourselves of some of the expectation values which we calculated last week. So one of them, which we're going to meet again, was this expectation value here, or this is actually not an expectation value, it's a transition matrix element. So we calculated the transition matrix elements from one particle, one hole state to a given vacuum reference state. And we found that that was given by I, and this operator F of A. So that was one of the matrix elements which we calculated last time. We also calculated the matrix elements, the diagonal matrix elements between the same one particle, one hole excitation. And what we found in that case is that this was given by A minus, and we have an I and F of I plus the reference energy. We also calculated the matrix element between phi 0 and H and phi ij of A, B, and we found that one to be given by ij v AB anti-symmetrized. We did also calculate the non-diagonal one particle, one hole matrix elements, but I'm not going to repeat all of them here because we're going to bring some of them up. So we can now move over to a diagrammatic representation here. So let's look at how we could represent some of these terms diagrammatically. So I remind you of some of the rules which we had last time. So when we looked at the true vacuum, or the vacuum state, which we just label as 0, then the only contraction which was non-zero was a contraction between two states, AP, AQ dagger. This was the only non-zero contraction. What we had then was if we had two states, so we had a state Q leaving and a state P here. And then when we state Q here, then the contraction is typically labeled like this. And then we transform that one into a line with an arrow. What we also did was to label a one-body operator, this operator H0, that had a representation. So this is the same as this AP, AQ dagger, like that. So a one-body operator H0, which was given by the sum over P and Q, and we had a matrix element H0 Q of AP dagger AQ. That is something which we would label without any arrows because we hadn't done any contractions yet. So when we don't put arrows, these are now undefined. It's undefined whether we are particle states or states below the finite. So we would typically just put signs like P and Q like that. Similarly, the one-body operator. So when we look at this operator here, or this diagrammatic representation, we see now that the outgoing state is given by P, and the incoming state is given by Q. And then you can read off from this diagrammatic representation, you can read off the mathematical expression for the operator. Then what we would have as the next case was the expectation value. So if we took now a state, which was now given by, suppose we had two particles, A1 and A2 here, like this. And then we have the one-body operator with P and Q. And then we have the same incoming states. A1, no, I'm not going to put arrows on them, sorry, because we haven't taken the contractions yet. So I was just moving one step ahead. And then we would have these ones like that. So when we are typically dealing with a true vacuum, we don't put arrows before we have done the contractions. However, this becomes a little bit too complicated when we're dealing with particles and holes, because then we want to indicate whether this is a whole state or particle state from the very beginning. And then we're actually going to put arrows on the equation. So this was a case which we looked at a little bit earlier. And then when we did the contractions, we could perform a contraction like this. And then what we got was a contribution which looks like this with an arrow A1, a state A1 here. And then we had a Kronecker delta, which is normally left out. So that means that when we look at this expression here, this is now given by a matrix element H, A1, H0 of A1. So the outgoing state, which is this state here, enters the brass side, and the incoming state enters the ket side. So when you look at such a diagram, you can then read off immediately the expression for the analytical expression for the matrix element. So what you would typically do then, you would label, when you have computed the contractions, you would then label all the states, the incoming and outgoing. And from the type of operator, you would then just read off the explicit analytical contribution. And then we had the two-body operator, which we called H of I, which was then given by 1 divided by 4. And then we had an AP dagger, AQ, AS, AR, and then a matrix element, PQ, V, RS, anti-symmetrized. In this specific case, when we look at the anti-symmetrized operator, this would now be given by this term, and then there would be an additional term. We would now have the exchange piece like that, and we normally put a plus sign when we're looking at diagram. But when we have such a crossing fermion line, that means that we have to add a minus sign when we deduce the matrix elements, and then we could now calculate the expectation value of the same. So let's just take away the lines here. So we would have a state A1, and then a state A2 coming in, and then a state A1 and A2 here. And then we can perform contraction. So we could take a contraction here. So we would have P, Q, and then we had RS here. And we can perform the contraction with this one. And then we can contract this with that, and this with that one. And we can do the similar thing with the exchange term. So what we got then would be something like this. So we have the outgoing lines A1, A2. So these are states above the Fermi level, or state not above the Fermi level, but states with respect to the true vacuum state, A1 and A2, and then all states are particle states. And then we would get a diagram which looks like this, where we have the crossing line here. And then we would have an A1, A2, and we have the two vertices, and then we have an A1, A2 here. And then we can read off the matrix elements immediately. So this becomes A1, A2, or V, and then A1, A2 here. And this second term becomes minus because we have two crossing lines. And that's because we actually have to exchange operators in the chain of contractions which we're having. So this will be A1, 2, A2, 1, or V of A1, A2. So this is the way these matrix elements will look like when we now are dealing with the true vacuum. Now, when we now move to the particle Hall formalism, then we have to make some changes here. And now I'm going to put arrows just to indicate that they have Hall lines. So that means that when I now move on to the particle Hall formalism, I'm just going to go away a little bit from this lines without arrows, because I want to make a distinction between a general particle state and a general Hall state. So that means that now, with a new vacuum, we are going to have states like an A dagger like this, and then we have the contraction with an AB. So this is going to be now a state like this. So we're going to put arrows in it. So we're going to have an A coming in here, and then this is the contraction, and this is a B here, and this is now the contraction, which is marked like this, and this becomes simply a state A. So this is a delta AA here. So it means that the particle line is going to have an arrow from the beginning. So previously I did not have the arrow. So normally this can create some confusion, but I hope that we are able to distinguish the different types of labeling here. And similarly, when we had the Hall state, we had an AJ. So this is the only contraction which we have. So this would now be a Hall state, J. So this would be a J here, an I. Sorry, this is an incoming state. Sorry. It's actually this one. So this would be a J, and this is an I. And we know that this one is given now by, it will be given by a line like this, where we have an I, or simply just a line with an I. And this is also the same as a delta IJ here. Actually, this is delta AB here. So if we now look at the calculations which we had for one of these matrix elements, if we now take a closer look at the expressions we had here. So let's now take a look at this contribution which you see here and see how we can represent that diagrammatically. So what we have when we look at the contribution from phi 0, H acting on this phi IA. So this is now going to contain the following terms. So it's going to contain a constant term, which gives rise to 0. This is the reference energy. So we will have to calculate the expectation values. So I'm going to put a proportional sign here. So I'm going to have this one. And now I'm having the operators AP, AQ. And then I have an AA, AI, acting on the vacuum state. Plus, and now I'm just setting up the, without the matrix elements, I'm just setting up the contractions which are needed for Wick's theorem. And I just leave out the summation signs and the explicit matrix elements, if that's okay. So this is a much more compact way of just setting up. And you will typically see that in textbooks, but people just single out the contractions you have to do, and then you go back, and then you plug in the Kronecker deltas and find the relevant matrix elements. So in this specific case, what we found was that if we take this contraction here, this is non-zero by definition. This is the only contraction when A is a particle state. I cannot do P with A because that's going to give us 0. I cannot contract AQ with AI. I cannot do this one because that's 0. This one is 0. And also, I cannot contract operators within the same normal order string of operators. This is Wick's generalized theorem. So this is what you see here is actually the only possible contraction which we can have. So that means that we have this term here. Then there is an additional term due to the two-body interaction, where we now have AP dagger, AQ dagger, AS, AR, of AI, of AA, and AI. In this particular case, since we have Wick's generalized theorem, we cannot perform contractions within the operator here. So what we would have then would be contractions typically of this type here. That would be an allowed contraction. And we could have a contraction like this. But what happens then is that I will have a contraction within the same operator, which is now going to give us 0 by definition. So this gives us actually 0. So the two-body term gives us only 0 contributions. So the only term which is non-zero is the one which comes from the modified one-body operator. So if we look at that one, what we have then is the following. So we are going to have a state, phi 0. So let's just write it out in a diagrammatic way. So there's a phi 0, which we normally leave out. And this is now multiplied with an operator here, with P and Q. And here I haven't put on any labels. And then I'm having a particle state, A, which I indicate with an arrow, and a whole state, I here. And this is then multiplied with phi 0. So one of the notations which you're going to see is a kind of more compact notation where we replace the vacuum state with just a line like this. And this is what the Hjorth and Bartlett is using and some other people. So you can choose to use phi 0 just to indicate that, because now everything is with respect to the vacuum. So if you go into the text of Hjorth and Bartlett, they would typically indicate the vacuum, which is double lines here. So that means that what you would have then is the operator here. And then you have the vacuum state here. And then you have a particle state and a whole state here, an A of I. So if you put labels, we have P and Q, and we haven't specified whether these are particles and holes. So the thing which we saw now from the contractions is that Q can now be contracted with A, like that. and then I is contracted with P. And that gives us this matrix element, which now is actually equal. So what we get is a matrix element of the type I of F of A. So the way we're going to write this matrix element now, when we now put in the contractions, this is in a diagrammatic form. It's going to look like this. So we have the state A coming in like this. And you see that from here. So we have an incoming state. This follows the same rules as we had before. So the incoming state is the one which is in a case state. And then we have an outgoing state, which is now a whole state, but holes of downgoing lines. So that means that this state here, this whole state is given by this state I. Now, if you wanted to represent this in the old way of doing that, what you would do now is simply to take the whole line and tilt it up. So in the previous case, when we had the true vacuum, this would look like this. Now, there's one thing now we have to be a little bit careful with. And that's the operator. So we just wrote generically F here by simply just writing it diagrammatically like this. But this operator F is actually not given by just one simple term here. So if you go back to the definition of the operator F, this becomes a little bit important. So if we look at the operator F now, that is given by this sum over P and Q. And now I have my P of H0 of Q. And then I have my, I'm just going to drop these curly brackets, of AP dagger of AQ. But then it has plus a P of Q of I here. And then I have the matrix elements, the two-body matrix elements, P of I of V, Q of I, anti-symmetrized, and then I have AP dagger AQ. So if we now look at the first term, so the first term which we have here doesn't have a summation over I. So if we now look at the way we would write the operator, so if we take the first term in a diagrammatic form, that would be now given by a sum over PQ, and then we would have the specific states, Q and P. But what is common to do is actually to skip the summation sign. So we will simply just write it like this. So this would be P, and there is an implicit summation sign over P and Q. Okay, so these are just notations. Then, if we take the next term here, we have to be a little bit careful with the states I, because this is an explicit sum over all the states below the Fermi level. And these are states which are defined as whole states. So now, what we are going to do is actually to rewrite this one in terms of a sum, actually, over I. So I'm skipping P and Q. So because this is implicitly assumed, so I have a P coming in and a P and a Q coming in without having specified them. And this is going to have this state I here. So I have already labeled that state I like this as a whole state. Now, what is common to do then is actually to replace this one with the following notation, where we just bring together the I's in a closed loop. Now, and then we keep the labels P and Q here. Then you have to remember that this sum contains also the other matrix element, which is now the anti-symmetrized matrix element. So it means that we could have a state which goes like this, an I here and a Q here. And then we could have a P here and an I coming in here. I and P. This is often now written, so the summation sign I is now translated into a closed loop. So this state here would now be, or this diagram would simply be written like this. So I'm not putting arrows. Sometimes it's tempting to put arrows on these states, but these are now unspecified, like that. So I would now close the whole line, and I would mark it like this. And then there's a state Q here and P here. So the fact that we have now these crossing lines gives rise to a factor of -1. And in this other case, I have a factor of +1. I have a closed loop and a one whole state. So that gives me one loop plus one whole state. That gives me a factor of +2. And to the power of minus the number of loops and minus the number of particles. I'm -1 to the power of loops and number of particles. I'm going to get a plus sign. So this diagram here is a diagram which then we are going to look at in more detail a little bit later. But this is the way we would typically write that operator. So if I now take only the so-called direct term here, that means that when I'm looking at the contractions, I would now have the true vacuum state, phi 0. And then I have my operator, which now would contain this whole state here, I. I have my P and Q, and then I have my vacuum state multiplied with a creation operator with state A and an annihilation operator in state I. So this is again my vacuum state here. And then I perform the contractions with this one and that one, and that gives me the following diagram. I, and then I have the state. So now I should be a little bit careful because I should put a sign J here because it's not the same. So I have an I state here, and I have an IA state coming in here. So this is how I would write that specific contribution. So it means now that if I look at the total matrix element IF of A, that is going to contain this term here. And then I have this one body operator. And then I'm going to have an additional term where I get a correction from the vacuum states. So all the filled single particle states now give a correction to the motion of this one particle, one whole state. And then I have an additional diagram where I now have this I, and then I have the exchange term, and then I have a state J here, and then I have my state I coming in here. State A. Sometimes I mix up A and I. Sorry for that. Normally, you can bring together these two terms into a fully anti-symmetrized diagram, and then you would normally just shrink it like this. So you draw the vertex, and then you have a J here, and you have an I and an A. So you bring together these two terms into just one, which represents both the direct term and the exchange term. So you can actually, when you have such a contraction, so let's do a final one before we take a small break. So when we look at this one, of H of phi I j a b, what we found last week was this was given by ij of v of ab, a and b anti-symmetrized. So let me just correct it here. So this is, if we're now going to look at that specific matrix element, so we have now the vacuum state, which I label like this. I have my two-body operator here with P, Q, R, and S. And now I have my vacuum state, which has A, these are particle states, and I have two whole states of I and J, like this. And when I perform the contractions now, what I did was actually to contract this one with that one. And then I contracted this one with that. And then I contracted I with P. And then I had Q with J. And that gives us a diagram which is going to look like this. So I have an I leaving, an A coming in, a J leaving, and a B coming in here. And that is not going to be the anti-symmetrized matrix element, but this is just the matrix element of V, of A and B. So what many people often do when you get some experience here under your belly or under your belt, so you what you would end up doing then is simply to look at these contractions by drawing diagrams. And then you just link the different legs. And then when you have done that, when you link the different legs, then you reduce that to a specific wave diagram. And from that specific diagram, you can read off the analytical contribution. So when you get some experience, this is often the way many practitioners actually calculate the expressions. And there's a whole field where you look at graph theory and diagrammatical representations, where you can then use that to compute all the diagrams which are allowed at a given order in the interaction. And from that, you can just read off the contributions.
Without making all the nitty calculations.
Yeah. Let's take a small break, eh? And then we will continue after the break, because now I wanted to... So one thing which we're going to do now before we move on to full configuration interaction theory is to try to wrap up this intermediate diagrammatic discussion. And there is a diagram which we haven't discussed yet, and a contribution which we need to take a look at. So if we now go back to the calculation of the vacuum to vacuum expectation value, what we found is that this is a quantity we are going to call the reference energy, because we have a reference state. And it was given by a sum over I, all the states below the Fermi level. And then we had I of H0 of I, like this, plus the two-body interaction. And then we have a sum over I and J, and then we have the Ij, Vij. And now instead of writing these anti-symmetrized matrix elements, I'm simply going to write out the matrix elements and Ij here, like that. Now, if you look at the diagrammatic representation, what we have is now a term. If you look at the first term here, that is going to be given by, since we have a whole state here, so we have an incoming whole state and an outgoing whole state. So when we have a whole state below the interaction line, then this is an outgoing state, because if you can just think of you flipping these states up like this, and then you see immediately, in this case, this is I and I. So the outgoing state is the one below the interaction line. But just think of you flipping these up and down, this up, this down, and this up, and then it becomes equal to that diagram. So it takes some time to adjust to it, but this diagram is something which actually looks like this. So we have a sum over I, which means that since we now have defined the sum as this closed loop, then this would simply be given by a diagrammatic representation like this. And now you see that if we now take the two-body term, what we have then, if we take the next term, so let's just put the arrows down here. If we take that one, we have a sum over I and J. And we would then have a whole line coming in and a whole line leaving. So this would have, I'm putting the labels now because I have done all the contractions. And this is J and J, like that. And then I would have minus actually plus, because we are not going to specify the signs when we look at diagrams. We read off the sign when we want the analytical expression for the diagram. And in this case, the way this one looks like, since it's an exchange term, it's going to look like this. So we have an I here, and then we have a J. So this is this is a state J, and this is state I. And then I have my I and J here, like that. That's one way of doing it. Or I can take the opposite. I can look at the lines below the interaction levels. Now, since we have a sum here over I and J, these diagrams are normally then compacted in the following way in terms of closed loops. So this is to indicate that this is a whole state which comes in and leaves. And we are summing over all the possible states below the Fermi level. And then we have the next one, which now would be given by the following. So we have a line like this, and then we have another whole line like this. And this is now an I or J, and it's irrespective whether you put I and J below or above. So this is a kind of compact notation which you would find. And then you can write the anti-symmetrized matrix element, and that would now typically be just one vertex line, so you shrink it, and this is often just written or drawn like this with an I and a J here. So that's a compact notation. So instead of calling this Feynman-Gaussian diagrams, that would be called a Hugenholz. So you have a very compact way of expressing this reference energy in terms of diagrams. And when you have this diagrams, you can just read off the analytical expression immediately by using the diagram rules which we have been discussing. Later, when we come to many-body perturbation theory, we are going to add some additional rules. And these rules is about the number of closed loops and the number of whole lines. So the sign which you get from the diagrams is given by -1 to the power of the number of holes and number of loops. So n is the number of loops plus a number of holes in the diagram. So the first diagram has 2 closed loops and 2 whole lines. So that gives me -1 to the power of 4, which is +1. And then we read off a plus sign. And this is simply to do with the way we do the contractions. Then the next one, which has a crossing whole lines, has just 1 closed loop. So you can actually view this diagram, the second one, as a diagram with 1 closed loop and 2 whole lines. So that would be -1 to the power of 2 + 1, and that is equal to -1 to the power of 3, and that gives a minus sign. So this is an additional rule which we will get more use of when we are coming to many-body perturbation theory and copper cluster theory later.
So you actually count the loop in the second one as well?
Yeah, that's a closed loop. That's just 1 loop. So a loop is either a closed loop with a fermion or a particle or state entering the same vertex and leaving the same vertex. Or you can see this one as a closed loop here, where you have this state leaving here into that loop and then into that vertex and this into that vertex. And then you have 2 whole lines. Well, we are coming back to that. So now I just wanted to show you the way you get rid of the sums of the I's and J's and simply compactify everything in terms of these diagrams. And what is common is actually to leave out the labeling I and J and just draw the diagram. So what you will often see is just something like this. Let me just write it down here. So you just put the whole line, and then when you want the contribution, you will simply put the given labels on the states, and then use the diagram rules, extract the analytical expressions, and find the sign in front of the analytical expression, whether it's a plus sign or minus sign. Okay, so what I want to do now is actually to switch over to full configuration interaction theory. So that is FCI full configuration interaction. So every way we can now order a set of Slater determinants is called a configuration. So when you take and distribute n particles on a given set of single particle states, all the ways you can make these distributions with the replacements, they are called configurations. So the ground state, this ansatz we made, is a typical configuration. For one particle, one whole state is another configuration, and so on. So this is full configuration interaction theory. So let's now go through some of the basic details here. And we're actually going to need all these matrix elements. So what we have seen, we have defined the ground state, or this ansatz for the lowest lying state, in terms of a product up to n here, and then we are filling in all these single particle states. And then we have multiplied this with a true vacuum. This is the way we have defined it. And then we define this one particle, one whole states, etc. So let me just quickly remind you of that. So we would have an I of A, which is now simply an AI here, multiplied with this vacuum state which we have. So these are all n particle states. If I were to have two creation operators here, this would be suddenly n plus 2 many-body states. Now, one of the things which we also have to keep in mind is that this set of Slater determinants, if I have a Slater determinants IA of phi j b, this gives us delta AB, delta ij. More generically, these Slater determinants which we have constructed are assumed to be orthogonal. So if we have a general many-body state, so let's just write this as a phi of alpha, and a state lambda, these states are assumed to be orthogonal. So that means that when I do this, I have a delta lambda alpha. So if I now look at the way we can organize this ground state, suppose we are looking at the ground state now. We are not limited, so I'm just looking at the ground state. What we did in the beginning here was to simply rewrite that one in terms of a sum over lambdas. So I have the C lambda 0, and I have this basis of Slater determinants. So my basis, phi, is a complete orthogonal basis, and I assume it's also normalized. What we can do then is to rewrite this in terms of particle-hole excitations. And this is the way we are going to partition the configurations. So in our case, we are going to write this as a C00 with a phi 0, like this. But then I'm going to change the labels a little bit. So I'm going to just call this quantity for C0. And we are now going to look at the sum over all the one particle, one hole excitations. So we are just reordering this specific sum here in terms of one particle, one hole, two particle, two hole, up to n particle, n hole excitations. So that means that what I'm going to have now is a new coefficient, which I'm simply going to call a coefficient CIA, multiplied with this phi a like this. Now, these coefficients are now, in a way, tailored to the reproduction of this ground state, psi 0. So if I take another state, if I have a state here, which has a j here, for instance, then I would have to have other coefficients. So let's suppose now we are targeting the ground state. But the formalism you see here is not limited to the ground state. This could be any state which you can construct from this specific Hilbert space of the phi's which you have here. But now suppose now we focus on the ground state. So we would then have a sum over A, B, I, J. So we have the new coefficient C, I, J, A, B. And we multiply that with this new Slater determinant of A, B, and so on. And this goes up to the n particle n hole. So then now I'm just going to go to this A1, A2 up to AN. And then I have an I1, I2 up to IN. And then I have the coefficient CI1, CI2 up to IN. And then A1, A2 up to AN. And this is now multiplied with this new Slater determinant, which represents all these n particle, n hole excitations, A1 all the way up here, like that. So we are going to rewrite this now in terms of a new operator. So we have a C0, which is a constant. And then I put a hat because now what we have here is actually an operator, because these P, I, J, A, B's, and so on, they are given in terms of creation and annihilation operators, multiplied with phi 0. So if you now look at one of these terms, AI, CIA of phi I of A, this is actually given by AI, CIA, which is a constant, and then A dagger A, AI, acting on phi 0. So that means that these terms which you see here can actually be rewritten in terms of a constant, the ansatz for the ground state, and multiplied with a chain of creation and annihilation operators. And that's why I write this C here as a hat. So this quantity which you see here, this C hat here, is normally called the correlation operator. And clearly the role of these additional terms becomes important if you have a poor approximation to phi 0. So if phi 0 is a bad representation of psi 0, that means that the other terms will actually have a non-negligible contribution there. So if we now look at the eigenvalue problem, so the way we are going to rewrite this one, so I'm going to rewrite this psi 0. This is now going to be given in terms of all the particle hole excitations which I can have. So I'm going to write this as CH of P multiplied with a phi H of P. So this is the more compact notation for this specific sum which we put up here, where H and P now can represent a 1 particle 1 hole, 2 particle 2 hole, 3 particle 3 hole, and so on. And then I have to break it down if I look at the 1 particle 1 hole to the specific indices. So is that okay? So when I'm calculating the energy now, so the ground state energy, and I'm just going to call this for E to distinguish it from E0 reference. This is the expectation value of psi 0 of H of psi 0, right? Which means again that we can rewrite this in terms of a sum over PH prime, like that. We're going to have a coefficient CHP, complex conjugate, and then a coefficient CH prime of P prime. And then I have the specific matrix elements between these various states which we have here. So this is nothing but me plugging in the definition here and just setting up the expectation value for this specific ground state using the computational basis which we have. Now, what we know is also that this kind of problem, this E0, or this energy problem here, if you now think of I don't know if you remember from linear algebra theory, when you look at eigenvalue problems, this is given by the so-called Ritz coefficient, and which is then defined as psi 0 of H, psi 0, and in case this is not normalized, it's given by psi 0 divided by psi 0, like that. So what you typically do now, when you want to optimize this problem, is that you calculate the derivative of this quantity with respect to these unknown coefficients. So this is a problem which you typically want to optimize. This follows also from the variational principle that you have here. And you will typically rewrite this in terms of a parameter lambda. So what we end up doing then is actually to calculate, and since these are complex, it's a complex conjugate parameter, these are assumed to be independent of each other. So for us, it's sufficient to actually look at the derivatives with respect to one of these. So these two problems, they are, so these are complex conjugates, and a necessary and sufficient condition is actually to require that the quantities that multiply with the complex conjugate quantity are those which we can set to vanish. So when we want to optimize this problem, this is actually what we end up doing. And when you're optimizing, what you can do is actually to simply multiply out the denominator, and then you end up with taking the derivative of a following quantity. So when you do the calculations, then you end up with a sum of P and H prime, and you've probably seen this before in different math and physics courses. So you would have a sum, we take the derivative with respect to the complex conjugate, and then I have an H of phi of H prime of P prime, and this has a C of H prime of P prime, and this is then given by this term E multiplied with a C of H prime of P prime, and then I have my states phi of H of P and phi of H prime of P prime here, like that. And then this is divided by constant, which I actually put equal to 0. No, not put to 0, but it's just a constant, which is the normalization factor squared. So the term which if you now look at what we have here, there's we should be a little bit careful here, because if we assume that the basis is not normalized, not an orthogonal basis of the phi's here, then we would actually have to calculate that, set up this matrix. This will become a matrix. If we assume that we have an orthogonal basis, this just reduces to just a Kronecker delta, and then we just have E times C H prime of P prime of H of P. So in general, so if we now assume, so let's just make a more compact notation here. So let's let this PH go over to an index I, and then we let the PH prime go over to an index J. So I'm just going to rewrite this in a more compact way. So that means that the matrix element which I have of HP of H of phi of H prime of P prime is equal to something which I'm going to call IJ here, like that. So that's just a matrix element. Okay. And we know how to calculate these ones now. When we use Wick's theorem, when we are setting up these different excitations, we can always calculate these matrix elements pretty easily. Then we also have to be a little bit careful with the overlap which we have here, this specific overlap. So let's come back to that one, but let's look at this term here. So since I have PH prime, P prime and H prime, this is now replaced with a symbol J. So this becomes a C of J. Then I have to be a little bit careful, because I may not have an orthogonal basis. So let's just take the general case now. And this is an overlap matrix, and this is just given by an Sij. So clearly, if I have an orthogonal basis, this just reduces to Kronecker delta. But let's now assume that this is not the case. So what we have then is that when I take the derivative of the energy with respect to this C of I complex conjugate, what I have now is a sum which goes over J. I have my J, and then I have my Aij minus this energy of Sij, and we want this one to be 0. So that means that what I have now, if I now assume that Sij is a Kronecker delta, delta Ij, let's do that. Then this reduces just to J of Cj multiplied with Ij equal to Ci multiplied with E. Does that sound plausible? And this is a standard eigenvalue problem. So this is nothing but, if we rewrite it, this is nothing but H. If we think of this as a matrix now, so this is a matrix, so I'm not putting a hat on it just to distinguish it from an operator. So this is a matrix multiplied with a vector, and that is equal to the eigenvalue multiplied with a vector. So keep in mind now that these Cj's, they are now representing the given eigenvectors of the system. Is it okay? Everybody's nodding their heads, but you always have to be sure that you.
Yeah, one thing I don't remember, why are we taking the derivative with respect to the C complex conjugate?
You can take it with respect to the other one.
This is
So you get the same because there's the two equations which decouple.
okay.
Because they are, I mean, you can actually see that you can actually show that they are independent of each other. So you can look at the derivative with respect to the complex conjugate or with respect to the other one.
In this case, this one is simplified.
Yeah, yeah. So what it means now, since all these configurations represent different types of excitations, let's try to write this down in terms of the states which we have defined. Okay. So we can now set up this is a matrix eigenvalue problem. So let's now set up the matrix H. So what you have is a phi 0, that's one of those states. And then we have the phi Ia, one particle, one hole excitation. We have the two particle, two hole excitations, Ij, Ab. So this is 0 particle, 0 hole. 1 particle, 1 hole. This is 2 particle, 2 hole. And then you continue till what I'm going to call just an n particle, n hole state. And I'm just going to write this as a Ij like this, and Ab. So this will be that specific block of the matrix. And then when you go down here, what you have is a phi 0 to multiply. So I'm setting up the matrix elements which you have here. And this is a phi A, and a phi Ia. This is the 2 particle, 2 hole block. And this continues all the way here. So I'm just setting up the matrix. And then we have the 3 particle, 3 hole block. There is a 4 particle, 4 hole block. And then we go all the way down to n particle, n hole blocks. And then this is now multiplied with the vector C. So we are going to have coefficients of the type C0. There's going to be a C, and I'm going to write this as a 1 particle, 1 hole. A C, 2 particle, 2 hole. And all the way down to C, n particle, n hole. They can actually be many because we said that we had an infinity of such states for each block. So 1 particle, 1 hole, if you have an infinity of single particle states, actually we have an infinity of states here. So that's where we will truncate. So we will actually always define an effective Hilbert space. And that obviously leads to their own problems. But in principle, what we do now, we assume that we can actually deal with a finite basis. And that means that the matrix is finite. So that means we have a finite vector. And this is just equal to E times the states C, one particle, one hole, etc., all the way down to n particle, n hole, like this. And now you see that what we need is actually to set up these matrix elements. So if we can set up the matrix elements, then we diagonalize this matrix, because what we need is actually det of this H minus E times this overlap S equal to 0. In our case, we assume that S is just given by a diagonal matrix with Kronecker deltas. We have assumed on a orthogonal basis, and that makes life simpler. So the only thing we need to find now is actually the eigenvalues of this matrix H. And this is basically FCI. And now you see that with Wick's theorem, we have actually calculated all these matrix elements. So we know what they look like, right? So the interesting thing for us now, when we are setting things up, is that we can now, if we have a two-body interaction, we know exactly what this matrix is going to look like. So let's now just look at the structure of this specific matrix organized in terms of one particle, one hole, two particle, two hole, etc. excitations. So if you look at this matrix, and I'm trying to use these bold-faced symbols here to indicate that this is not the operator anymore, but it's the matrix. What we would have then is a matrix which goes like 0 particle, 0 hole, 1 particle, 1 hole, 2 particle, 2 hole, 3 particle, 3 hole. So these are blocks now of elements. And this goes all the way up to n particle, n hole. And then we have the simulus on the side here, 0 particle, 0 hole, 1 particle, 1 hole, 2 particle, 2 hole, 3 particle, 3 hole, and all the way down to n particle, n hole. And then we have matrix elements here. So if we look at the general structure here, and we have a two-body interaction, operator, you can just write it as a two-body operator at most. That means that here we will have a matrix elements which may not be equal to 0. The same here, the same here. But here we have actually more than two single particle states which differ from the state 0 particle 0h. So if you look at that element, we would have the overlap between this state of H and a state which now has 3 different single particle states. And we know that that is 0. This goes back to one of the exercises we had in the beginning of the semester. So it means that all these elements here have to be 0. Now, when we look at the 1 particle, 1 hole, we saw that that does not need to be 0. We can have a diagonal matrix elements here, as we showed. We also have something which is non-zero here. And now, since in this case, we have now a 1 particle, 1 hole excitation, there can in principle actually be 2 states which differ. So this is normally non-zero. But if I have a 4 particle hole, then there will be at least 1 state which will be different. And this will be 0. So that means that we can go like this, and we have zeros all the way down here. This goes like this, and it has zeros all the way down. The 2 particle, 2 hole can actually link with a 4 particle, 2 hole, but then it's 0. Like this, and then the rest are zeros. So you see that there's a structure here. The matrix is actually band diagonal. And the larger the number of particles you have, the sparser the matrix. Because then clearly if you have 100 particle hole excitations, then there will be tons of matrix elements here which are 0. So this is the basic structure of the matrix which we have. Now, what we are going to do now is actually to bring back the calculation of the matrix elements, because we found that we have phi 0 of H. We cannot plug in the values. So this is something which we call epsilon 0 ref. We have the value for that one. We found phi 0 of H of this matrix element, so we know that block. So I of F of A, so we have an analytical expression for that. And that means that we can go in and fill up this block. Similarly, we know the value of this matrix element with that. And we found that phi 0 with H of phi ij AB is actually given by ij v AB. And all the other ones will be 0 when we link phi 0 with these different states. So that means that we know the analytical expressions, and when we need them to set up this Hamiltonian matrix, we know exactly how to compute them. And then we can just fill in the matrix elements. And that's extremely handy. And you see now that Wick's theorem, since what these matrix elements are, they are matrix elements between many body states. And having redefined the vacuum states now allows us to calculate in an expedient way the contributions to all these different blocks. Now, tomorrow, what we are going to do now is to rewrite this. Instead of an eigenvalue problem, we are going, so the eigenvalue problem which you have here, if you can set it up, you can diagonalize it immediately. So we are going to do that with a Lipkin model, and we are going to see what the eigenvalues mean and what the different matrix elements mean. But then we can actually rewrite a diagonalization problem in a much inefficient way in terms of nonlinear coupled equations in the unknown coefficients. So remember now that what we are doing here, we have a computational basis, and by diagonalizing, we get the unknown coefficients here. So the diagonalization gives us the exact ground state in that basis. So keep in mind, it's not the exact. If somebody gave you the exact one, this may not be the exact one, unless you have an infinite basis. But it's the, if you can diagonalize this problem, this is the exact solution within that computational basis. So that's the way you have to phrase this. Doesn't need to match what nature wants you to reproduce, but it could be a good approximation. But then you can actually solve these equations here, not by diagonalizing, but by rewriting an eigenvalue problem in terms of nonlinear coupled equations. And that is going to make the link with many-body perturbation theory, Hartree-Fock theory, and copper cluster theory. So you will see then how these coefficients can then be interpreted in terms of different many-body theorems. And that's pretty neat. That's a way which gives a kind of deeper understanding of the link between this, which is exact. It's the simplest possible way, right? So we have Wick's theorem. With Wick's theorem, we can calculate all these matrix elements. All of these can be set up immediately. You take any many-body Hamiltonian, calculate the matrix elements, plug it into the Hamiltonian matrix, diagonalize, and there you have the answer. So we normally say that FCI is the simplest possible many-body method you can think of, if you can calculate and diagonalize. And the reason we bring it up is that it serves as a reference for all the other many-body methods.
If you had a three-body operator instead, you would just add a diagonal along.
Yes. So with a free-body interaction, you would get this term, non-zero.
So you just add diagonals.
Yeah, exactly. And that gives you a matrix which becomes larger, but still, if you have tons of particles, it means that it's still, the matrix will be sparse. So now you can say that if you use second quantization in a new vacuum state, you can use that to calculate these matrix elements in an expedient way. So that's the benefit of using second quantization.
It makes sense.
Yeah. So now you start seeing, when you see the many-body context, you start seeing the why Wick's theorem, Wick's generalized theorem and second quantization gives you a tool to calculate these matrix elements in an expedient way. And at the end, you just draw diagrams. And you can give a physical interpretation to the diagrams, like a two-particle two-hole excitation, or one-particle one-hole excitation, and so on. And you know, when you diagonalize, this is something we will discuss a little bit tomorrow, but I won't anticipate it. When you diagonalize, what you're doing is that you're finding a unitary transformation, which brings this matrix into diagonal form. Now, Hartree-Fock theory is a unitary transformation itself. But what you're doing then is just to set these matrix elements to 0. All the other ones are non-zero. And the hope then is that the link between these ones and these and so on is much smaller than, or that you can even ignore it. So you can interpret many of these methods as types of unitary transformations. That's another way to read different many-body methods. Okay, I'm going to stop the recording here now, if that's okay with everybody.